Okay, folks, ready to dive deep. Today, we're looking at this paper, Emergent Symbol-like Number Variables in Artificial Neural Networks. And it's got everyone buzzing, pun intended. It's all about how neural networks, those AI systems we hear so much about, actually deal with something we take for granted, numbers.
Yeah, it really is a fundamental question. I mean, we learn to count as kids, but how do you even begin to teach machine to understand numbers? It's not exactly intuitive.
Right, like we can tell a computer to add 2 and 2, but
Yeah.
does it really get what 4 represents? This paper goes beyond just, arithmetic and looks at how networks represent numbers, like conceptually.
They're looking at numerical equivalence. Can a network understand that 5 apples and 5 oranges are the same amount, even if they're totally different things?
That's a great way to put it.
Yeah.
So how do they even go about testing this?
Well, they use this framework called next token prediction. Basically, they train different types of neural networks, RNNs and transformers, on tasks where they had to predict the next item in a sequence, like based on some kind of numerical pattern.
Oh, okay. RNNs, those are like the step-by-step thinkers, right? Processing each input in order.
Exactly. And then you have transformers, which are more like taking in the whole context at once, seeing the forest for the trees, so to speak.
Gotcha. So they train these networks to be like pattern detectives with numbers, and then what? How did they peek inside to see what was happening?
They use some really clever techniques, combining causal interventions, so like tweaking parts of the network to see how the output changed, and analysis methods like DAS to try and decode well, you could say the logic behind how the network was solving the problem.
So they were basically trying to figure out how the network was thinking about numbers while it was doing these tasks. What did they find? Did these networks actually develop a number sense?
Well, what's amazing is some of them did. Just by doing this next token prediction thing, they seem to create what the researchers call number variables. Like they were coming up with their own internal code for representing and working with numbers.
Wow. So are these number variables as precise as like the numbers we use in math? Are they, perfect representations?
Not exactly. They have what they call gradients, which basically means their understanding of larger numbers or like bigger differences is fuzzier. It's a bit like how, little kids might be great at counting to 10, but then things get a little iffy when you start talking about bigger numbers.
So like AI toddlers figuring out numbers. That's kind of cute, actually. But wait, doesn't that kind of mirror how we learn too?
Yeah.
I mean, even babies seem to have some sense of quantity even before they can actually count.
That's a really interesting point. And there's actually research showing that even people who don't have specific number words in their language still demonstrate some understanding of numerical concepts. So maybe these networks are tapping into something pretty fundamental about how brains, even across different species, represent numbers.
That's a mind-blowing thought. Okay, so we've got these AI systems showing signs of developing their own counting systems. And those systems seem to have some parallels with how humans think about numbers. Before we go too deep into the philosophy of all this, though, what's the takeaway for AI research? Like, what does this tell us about how to build better AI?
One big takeaway is that the size of the network seems to matter. Bigger networks were much better at developing these symbol-like representations. So as we keep building larger, more complex AI models, we might see even more human-like reasoning emerging.
So bigger is better when it comes to AI and numbers. I wonder if this ties into like the lottery ticket hypothesis at all. That idea that within a big network, there's a smaller, more efficient subnetwork that can do the same job.
It's a good question. And yeah, it's possible. Maybe these larger networks just have more like pathways or combinations to work with during training. So they're more likely to stumble across these effective symbol-like ways of representing numbers.
It's like having more options leads to more sophisticated solutions, even if it's a bit roundabout. So it's not just that these networks are crunching numbers. They're developing a deeper, more abstract understanding of what those numbers actually represent. And the bigger the network, the better they seem to get at it. Pretty remarkable stuff.
It really is, and there's still so much to explore, like how these different types of networks, the RNNs and transformers, actually approach these tasks.
Oh, right. They each have their own thinking style, so to speak.
And their approaches are fascinatingly different. It really gives us more insight into like the potential and the nuances of how AI might be developing its own number sense.
Yeah.
So yeah, it's really interesting how those different architectures, like RNNs and transformers, how they each handled those numerical tasks. It's kind of like watching different problem-solving styles in action.
Okay, so lay it on me. How did their approaches actually differ?
Well, you remember how we were talking about RNNs, those step-by-step thinkers? They seem to really favor this, what the researchers called a count up, count down kind of strategy.
So they were like really keeping track, like adding and subtracting in their heads as they went through the sequence.
Pretty much, like they had this internal counter that they'd, increment or decrement based on the input they were seeing. Very methodical, you could say.
That makes sense. And what about the transformers, those big picture thinkers? How did they approach it?
Well, transformers, as you said, they're all about the context. They didn't seem to rely as much on this kind of like step-by-step accumulation. They were more about referencing the whole context of the sequence at each step.
So they were constantly like reevaluating their understanding of the number based on everything they'd seen so far, not just focusing on individual element.
Exactly. It's like they're considering the whole tapestry, right?
Yeah.
And not just individual threads.
I love that analogy. So, okay, two very different approaches, but both leading to this understanding of numerical equivalence. There was this same object task mentioned in the paper, though. How did they handle that?
Yes, of a same object task. This one's interesting because the networks trained on this task didn't show as strong an alignment with any of the symbolic algorithms that were proposed.
Oh, so they kind of struggled with this one. What made it so tricky for them?
Well, it seems like when the demonstration and response tokens were identical, they had a tougher time with that concept of numerical equivalence.
So, like, if it was all the same object, it was harder for them to isolate the idea of, like, how many.
Yeah, it could be that, without those different token types, it was harder to really separate out the counting process from the rest of what was going on.
Makes sense. Like trying to count the number of, I don't know, the letter A in a string of all A's. Your eyes would probably just glaze over.
Exactly.
Oh, no.
But without those distinct markers, that idea of quantity gets kind of lost.
Okay, so the same object task shows us some interesting, I guess you could say, limitations in how these networks understand numbers. Seems like there's still a lot more to uncover about how these number variables really work and how they generalize to different situations.
Definitely. It's like we're just starting to scratch the surface of how AI systems might be able to represent and work with numbers. It's really exciting stuff.
Yeah, and that brings us to the big question is, what does all this mean for, the real world? If we can create AI that really gets numbers, what kind of doors does that open?
Oh, the possibilities are huge. Just imagine AI working alongside scientists, not just crunching data, but actually contributing to discoveries, like AI research partners.
Whoa, AI scientists. Now that sounds like something out of science fiction.
Maybe, but it's not as far-fetched as it seems.
Yeah.
Think about it. These AI scientists could help analyze massive data sets, identify promising research directions, maybe even design experiments. With their ability to grasp these numerical relationships, who knows what breakthroughs we could see in medicine, material science, climate modeling.
It's mind-blowing. We're talking about AI not just processing numbers, but actually understanding them in a way that leads to real insights and discoveries.
Exactly, going beyond just pattern recognition to a deeper level of comprehension.
Okay, but we got to be realistic too, right? I mean, these networks were mostly trained on pretty small numbers, like up to 20. We don't know for sure if these findings would hold up with, really big numbers.
You're absolutely right. That's a really important point. And we also have to remember that gradients we talked about, it suggests that these number variables, they're not like perfect replicas of how we think about math. They're fuzzy, they depend on context, they're still very much shaped by how they were trained.
Right, so plenty of room for more research and growth here. But even so, these findings are pretty exciting, right? They open up this whole new world of possibilities for what AI can do. But I think it's time to shift gears and get a little more, shall we say, speculative.
You mean it's time for novel notions. I was wondering when we'd get there. Always love a good thought experiment.
Me too. Let's step outside the box a bit, see what kind of wild ideas this research sparks. Okay, time to unleash those novel notions. You know that part of the show where we let our imaginations run wild based on the research we've been discussing?
Always a fun part, like where can this research lead us? What are the big, crazy what-if questions?
Exactly. So with these findings about neural networks and their number sense, what kind of unconventional research avenues could we explore?
Well, what if we trained AI on tasks that are like specifically designed to mirror how kids learn about numbers?
Oh, you mean like those classic developmental psych experiments? PJ's stages and all that.
Yeah, like we could design tasks for AI that kind of mimic those stages, start with really basic stuff like object permanence and then gradually make it more complex.
So like creating an AI preschool for numbers. I love it.
Haha, right. And by following this developmental path, maybe we'd see even more robust, more human-like number representations emerging in these AI systems.
And it wouldn't just be about making better AI, right? This research could also tell us something about how we learn.
Exactly. By watching how these AI systems figure things out, we might get totally new insights into how our own brains develop mathematical abilities.
It'd be like holding a mirror up to our own cognitive development, but using AI as the tool. Okay, so that's one novel notion. What other crazy research paths could we explore?
Well, let's zoom out a bit and think big picture. Imagine a world where AI, with this deep understanding of numbers, is actually working in fields like scientific research or finance or even like art.
Okay, now we're talking. AI scientists working alongside humans, making discoveries. AI composers writing symphonies based on math. AI architects designing buildings with, like, numerical harmony.
Haha, exactly. And it wouldn't just be about AI replacing humans, right? It'd be more like a partnership, using the strengths of both to do things that neither could do alone.
It's a future where AI isn't just a tool, but a collaborator, a partner in pushing the limits of human creativity. Pretty amazing to think about.
Yeah, definitely. Of course, we're being super speculative here. We've got to be realistic about the challenges and all the questions we still have to answer.
For sure, but that's the whole point of these novel notions, right? It's about exploring those what-ifs and letting our imaginations run free.
And who knows, maybe one of these crazy ideas will lead to some real breakthrough down the road.
Well, that's a great note to end on. It's been a fascinating dive into this paper, from the technical details of neural networks to these, mind-bending possibilities for the future.
It really has.
And as always, we encourage our listeners to check out the original paper. You'll find the link in the description. Let us know what you think and what novel notions this research sparked for you.
Until next time, keep those neural networks humming.